Random Walk Drift-Diffusion, RWDD, model. This section introduces the basis of the RWDD model and the modeling methodology used to describe the main simulation steps, i.e. the charge deposition induced by the passage of an ionizing particle at silicon level, the radiation-induced charge transport within the structure and the computation of the collection current on the collecting nodes. In the RWDD approach, an ionizing particle track crossing a circuit at silicon level is modeled as a series of charge packets, figure 1, spread along a straight segment whose length equals the ionizing particle range, R, in target material. The linear density of the charge packet along the particle track takes into account the non-constant linear energy transfer, LET, of the particle. Schramm tables are used to compute both let and range using appropriate numerical functions. The accuracy of this charge discretization is ensured by the degree of granularity that can be fine-tuned by selecting the packet size, in practice from 1 to 100 elementary charges. Cartoon illustrating the charge transport and collection processes after a 5 MeV alpha particle strike in a reverse biased junction. Its geometrical and electrical parameters correspond to the 65 nanometers node. The biased contact collects charges that diffuse in silicon and are accelerated by the electric field developed in the space charge region. Reprinted with permission from Glorieux et al., copyright 2014, IEEE. The transport of each charge packet starts immediately after the particle crosses the device, figure 1. For modeling the charge transport, the RWDD approach implements the popular drift-diffusion model, where the electron, Jn, and hole, Jp, current densities are computed as the sum of two components, the drift current component, first term, that is driven by the electric field, and the diffusion component, second term, that models the current induced by the gradient of carrier concentration. Jn and Jpair given by. In these equations, N and P are, respectively, the electron and hole densities, micronewton and mu P are, respectively, the electron and hole mobilities, E is the electric field, and dN and dP are, respectively, the diffusion coefficients that may be calculated from the carrier mobility using the Einstein's equation. N, 3, Kb is the Boltzmann constant and T is the carrier temperature, as the carrier gas in the drift diffusion approximation is assumed to be in thermal equilibrium, T is equal to the lattice temperature. The next calculation step in conventional full numerical methods, TCAD, is to inject the current densities given by Eq. 1, and 2, into the conservation laws for electrons and holes, also called continuity equations. They are next self-consistently solved with Poisson's equation. For this purpose, the simulation domain is meshed, and all previous equations are discretized on this mesh grid and then solved. Contrary to this procedure, in the RWDD model, no meshing is needed since charge packets have continuous coordinates. Also in RWDD, a random walk algorithm is used to model the diffusion process, and the drift-induced current is directly calculated using the electrical field present in the considered region. For a charge packet situated at the position, x, y, z, at time t, its new position at time t plus delta t is given by x plus delta x, y plus delta y and z plus delta z, where dx, di and dz are calculated as follows. N4, N1, N2 and N3 are three independent normal random numbers, d is the diffusion coefficient, mu is the carrier mobility, and Ex, A, Ez, is the electric field vector at the corresponding position and time. At each time step of the simulation, the radiation-induced collection current is computed from the transport dynamic of minority charge carriers described in the previous section 2.2. For the estimation of this current, two main procedures may be employed. The first technique is to use the semiconductor transport equations, and the second one is to employ the Shockley-Ramos theorem. Simulation tools used in microelectronics generally consider the first option. The transport equations are implemented in TCAD simulator that numerically solve them self-consistently with Poisson's equation. This approach considers the free charge carrier distributions as continuous functions in time and space coordinates. The second option is generally used in instrumentation or high-energy physics for the calculation of detector responses to radiation events. In this second approach, the Ramos theorem is used to treat each carrier considered individually, and all the interesting effects due to particular carriers are summed. In our work, We implemented the first formalism, transport equations, by applying the continuity equation at the collecting, drain, contact. The transient current at the collecting node is directly computed from the number of carriers delta n that reached this contact during the time step delta t, i.e. In this expression, the displacement current is neglected, that is a reasonable approximation in this case. This collection current is then injected in the electrical simulation to model the circuit response. Although the model embeds a microscopic physical description of charge generation, transport and collection, the present approach suffers from two evident limitations that should be amended in a future enhanced code version. 1. The calculation is not self-consistent with the electrostatic potential, i.e. the electric field, and 2. It does not implement electrostatic interactions taking place between charge packets. For this reason, the RWDD model should especially fail in high carrier injection conditions, i.e. at high LETs. These drawbacks will be carefully estimated and quantified in a future work. Another interesting point should be to compare the two methods for computing the collection current to also evaluate the impact of the displacement current on transient characteristics.